I think we're probably going to get started. Alright, hey everybody, my name is Adam, and this is Braden, and this is our talk, Finding a Weak Link, Attacking Windows OEM Kernel Drivers. So today, we're going to talk about some of the reasons and motivations why we came up with this research, and also a methodology that was emerged as a result. We're also going to talk about some of the fuzzing tools and techniques that we use during this process, as well as a new reverse engineering tool we created to help aid in the process. Finally, we're going to talk about some of the bugs that we found in some OEM kernel drivers, and with any luck, we'll have some time left, and we'll fetch questions. But first, a little about us. Both Braden and I are security consultants at NCC Group. For people that don't know, NCC Group offers penetration testing services and other security-related services. Basically, they pay us to break stuff, which is pretty cool. We're mostly interested, in kind of like native application security and reverse engineering. Fun fact about us is that we both attended and graduated from the University of Oregon. Now, before we even got started in this research, we kind of noticed that most of the information that was sort of laid out for kind of going after Windows kernel bugs was targeted towards two specific audiences. Either kernel driver developers that have been doing it for several years, or kind of like your first Hello World program you just finished yesterday. To us, this didn't really seem like the best audience choice for these kind of attacks, and this was kind of our motivation to create our own methodology. So we decided we wanted to make a methodology that somebody that had some native application security experience, but maybe not necessarily has gotten down in kernel land, could use to find some Windows kernel bugs. And so we did some brainstorming, and we came up with 3 specific goals that we wanted to satisfy. The first one was obviously we had to kind of create this methodology, and we focus on making it easy to do, reproducible, and sort of somewhat efficient. And in order to realize that goal, we knew that we were probably going to have to either create some new tools or modify some existing ones. And then finally, of course, no methodology matters if we don't have any bugs. And so in that case, we wanted to make sure that we were specifically going to find bugs in fully patched Windows 10 installations. So where do you even begin starting when trying to create that kind of methodology? Well, I know how we did it, and we basically began by asking ourselves some really simple questions, such as, well, where are bugs most likely going to be found? And since we're kind of, naturally looking at Windows kernel drivers, you might think, well, what about Microsoft drivers? Well, and this is not necessarily the worst thing to think about. I mean, they are going to be present and prevalent in any Windows installation, and additionally, they have had issues in the past. That being said, Microsoft has done, some very recent things to improve their driver security model, and based on this thing, you can still find bugs in Microsoft drivers, but their rigorous security development lifecycle definitely makes it less of an easy target. On the other hand, OEMs, they don't necessarily have that same level of security extended to them, and so we chose them to be our targets. So the sort of the natural second question that follows from that is, okay, well, how are you going to find the bugs? And kind of keeping along with the methodology of an efficient, easy to do, and reproducible process, we decided to go with minimal effort bug hunting, aka fuzzing. And then sort of a final question we asked was, okay, well, other people have stuff that they've done in this area, like methodologies and so on and so forth. How can we improve upon any of those existing processes? And we decided that we really wanted to create a tool to sort of help automate some things during the reverse engineering process, and we were hoping that this would help satisfy that question. So we have our second goal. We wanted to create or modify some existing tools, and since we knew that we were going to be doing fuzzing for our bug hunting method, we were like, okay, well, we have 2 choices. We can either create a new Windows kernel driver fuzzer, not happening, or we can modify an existing one. And so we obviously decided to go with modify an existing one, and we focused our time on extending its functionality with extra features and bug fixes. And then the second idea was, of course, we wanted to create this tool, and so we decided we were going to create a tool to help with automating the reverse engineering process and using an IDA Python plugin. And then finally, obviously the most important goal is we wanted to find bugs in fully patched Windows 10 installations. If we didn't find those bugs, the methodology would sort of be worthless. It's like, hey guys, we did all this research, but check it out, we didn't get any bugs, so you should totally try this. No one's going to go for that. But luckily, we did go through and we did follow like sort of this methodology, and we were able to locate some bugs. And so I think so far we can say great success. Now, we've kind of talked about sort of the motivations of why we did this research and, you know, our outline of our methodology. And we know we're going to attack OEM target drivers, and we know we're going to use fuzzing. But first we have to actually have drivers fuzz, so where the hell are they? Well, luckily, Windows can help us out with that particular task. Built into Windows is a tool called Driver Query. And basically what Driver Query does is it will output the drivers loaded into the system. So here's a picture of Driver Query doing just that. Particularly the /SI flag is important here because that tells Driver Query to output who signed the driver. And so in this case, the OEMs that we're looking for. And another tool that we used as part of this process was WinObj. Now, WinObj isn't an actual tool that's built into Windows, but it's free, publicly available, either as a standalone product or as part of the sysinternal suite written by Mark Resinovich. And you know, WinObj does a ton of stuff. I'm not going to go into all this functionality. It's mostly to do with like Windows objects in the system, but what we needed to focus on was its ability to tell us the OEM driver's device driver symbolic link. Now, what we wanted is we wanted that symbolic link so that we could pass it to our Windows kernel driver fuzzer as a way of using it to communicate and with that device driver during the fuzzing process. And so a little bit to talk about that fuzzing process, kind of device drivers in general, and the communication process. I'm going to turn it over to Braden.
Thanks, Adam. Yeah, so before we go any further, I should probably talk a little bit about drivers and how we talk to them in general, all that good stuff. So drivers are basically just a way for users to talk to devices or for the kernel to interface with whatever hardware it's sitting on. And one way you can talk to these from user land is via the device I/O control call. To take advantage of this call, what you're going to need is the symbolic links Adam was just talking about, as well as what's called an ioctl code. An ioctl code is just a 32-bit number which indicates to the driver which routine you want to target. Once you have this ioctl code in your symbolic link, you can just pass an input buffer full of whatever data you want. The driver will take it, do its thing, and then send you some stuff back in an output buffer. So now that we know a little bit about how we talk to drivers, let's figure out how we might take them down. So the first thing we're going to need to do is get those ioctl codes so we can talk to the various routines. Then we are going to use those to fuzz the drivers. Hopefully we'll get some crashes out of them, and then we can triage the crashes, maybe take a look at the drivers. If the bugs look like they're any good, we will try and build some exploits. So why do we have to brute force ioctl codes? It turns out that they're pretty rarely documented, so it's pretty much always on you to figure out what the ioctl codes are on your own. You can try to reverse engineer them out of the driver manually, but this can be time consuming because they can end up represented a number of different ways. So what we usually end up doing is we actually just guess every possible ioctl code, and we can kind of infer on how the driver responds to that. We can infer from how the driver responds to that, like whether or not it's a valid code. And so rather than roll our own ioctl brute forcer, we decided to go with DIVF, which is an open source driver testing tool suite that's on the ISEC Partners GitHub. And it was written by some of our coworkers, so I figured it'd be pretty easy to work with, because we can always just kind of ask them, like, hey, why does it work like this? And here's just kind of a quick picture of what it looks like in action. You can see it here at the top. It just goes through and just starts guessing every possible code, and then once it gets a few hits, it's like, hey, we think these ones are valid, and it spits all of the valid ones out. And in the background, it's also writing this information to a file, so in case it crashes along the way, you won't lose all your information, because sometimes you'll get crashes when doing this stuff. And so now that we have some ioctl codes, we can get to fuzzing. So there's a number of driver fuzzers already out there. IOSpy and IOAttack by Microsoft is one example. But since DIVF also has fuzzing built in, we decided to stick with it. And it turns out that DIVF is a pretty good fuzzer in its own right. It's multi-threaded and it's quick, so it'll actually shake out all the race conditions for you. It has a few different kind of cool input processing or input modes where it'll you do a sliding D word, or it'll just fill the buffer full of random data for you. But one nice feature it has is you can actually hook it up to a named pipe, and feed it data from like a smart fuzzer. So if you want to take like peach and make like a nice peach pay with like a smart generational fuzzer because you know what the input type is, you can actually take that and then hook it into DIVF to take advantage of the rest of DIVF's features. So it's nicely extensible in that way. And here's a quick shot of what DIVF kind of looks like in action. You can see down here at the bottom, after I hit Control-C, it starts to print out some stats about the requests for you. Although hopefully you'll never actually see the screen because you'll have a crash long before you give up and hit Control-C. And while it was a pretty good tool in its own right already, we did make some improvements along the way. One thing we did was make smarter brute forcing. So sometimes we'd run into the case where we'd run into hundreds of opto codes, which doesn't sound right. Usually there's not more than 20 or 30. And so we're like, hey, these are probably fake. It turned out a lot more bogus. And so we just kind of implemented some functionality to react to how a driver responds. Because it turns out they can respond however they want. There's no like set you have to. So it kind of tries to learn why what might be a valid opto code. We also implemented some kind of experimental functionality. We look in the output buffer to see if there's anything in there that kind of looks like a kernel pointer. And we also look to see if maybe the driver wrote outside of the bounds of the buffer, which should usually indicate that there's something going on with the driver. We also added functionality to like shove the size of our input buffer into the first D word of that buffer, which might sound kind of weird and arbitrary, but it actually turns out a lot of driver routines expect that. And in fact, one of the things we'll look at later does. We also just kind of did your standard fix-ups along the way. Clean up output to standard out, add some usability features, and neat stuff like that. Now that we have our fuzzer, one thing to keep in mind when you're fuzzing drivers is that it works differently than fuzzing stuff in userland. So, for instance, if you're fuzzing with something like AFL, you can get tens of thousands of crashes and restart the program fresh every time and just not lose any speed. However, when you're fuzzing something in the driver, or in the kernel, when you get a crash, it's going to bug check in your face and reboot your whole system. So it's a lot less throughput when you get crashes. Likewise, you can also get a crash that's caused by two requests that you sent hours apart because the driver is maintaining state this whole time. It's not restarting every time fresh like it would with like a fuzzer like AFL. And another thing is, since we're targeting OEM drivers, they expect the hardware to be there. These are drivers that are designed by the hardware manufacturer to interact with that specific hardware. So you can't very easily fit all this stuff into a VM, otherwise it's going to replace those drivers with, like VMware drivers or whatever. And so what you end up with is something like this, where you have a couple laptops sitting around and they're kind of freaking out and look like they're having a seizure because you're fuzzing on their power management drivers. And one last thing about fuzzing is you want to make sure you turn on driver verifier. Driver verifier is a built-in Windows tool that will force a crash when it detects misbehavior with the driver. And it does this through a few different ways. One thing it does is it puts all memory allocations into a special memory allocation pool, and then it checks to see if the memory gets referenced after it's freed, or if there's an out-of-bound read or an out-of-bound write that might not normally have caused an access violation, and then it'll force a crash, which is great because a lot of times those conditions can be made to be exploitable with a little bit of TLC. It also has a check to make sure that it's not, reading and writing from userland, and which can be helpful sometimes. Also do kind of some controlled mayhem. So you'll put the driver into low power mode, or you can put it into low memory mode, or you can just have random Windows API function calls fail. So this is a really, really good way to test error handling code paths that you might not normally hit, during the normal course of fuzzing. And those are usually conditions that you can recreate though. And with any luck, you will get something like this, blue screen of death. Although now they've redesigned it, maybe it's like the frowny face of sadness. We kind of wonder sometimes if maybe when they were doing the redesign, if they had some other ideas along the way, like your computer took a crack screen. Or maybe it's the kernel doesn't know what's going on screen. But whatever you call it, once you get some crashes, you need to figure out what happened. Why did the kernel blow up? Why is this fan inside of this KFC? These are all questions that demand answers. And so what you're going to want to do is throw that crash dump into a debugger, and this is going to be a chance to get your first guess at exploitability. Try to see what optocode was responsible for the crash, maybe what your input buffer looked like, and where the crash happened in the driver. And so for a kind of high-level view of exploitability, Microsoft has a plugin called Bang Exploitable. It'll kind of give you like a rough outline. Like for instance, it'll always say that a write violation is exploitable, but it is a bit rough, and you don't want to just be like, you don't want to take this at its word and just be like, yep, it's exploitable, we're done. So what you want to do is run Analyze. Analyze is great because it'll tell you all sorts of stuff about the condition of the crash. So you get to see like the call stack, so you can kind of see everything that was getting called along the way. You can see what the crashing instruction looked like, and it'll tell you what the access violation was. So, you know, if you get a write violation, that's usually a pretty good sign. But read violations can be good too, as we'll talk about a little bit later. And there's also a chance to kind of determine how much control you have over the crash. If your buffer like directly overflowed some stack buffer on the driver, you're probably in pretty good shape. But maybe, you know, the crash happened in some unrelated part of the system that you have no idea how you impacted. And so this is a sample, like a clip from the Analyze output. You can see down here, that's the offset of where the driver crashed at 183F. And so what we can do with that is we'll pop the image, we'll pop the driver into IDA and then rebase it back to 0. And then you can actually go to offset 183F of the driver and fire in IDA and see exactly where the crash happened. Which is super handy during your static analysis phase if you're trying to figure out where this vulnerability was, because sometimes drivers can be pretty immense, and so if you're just trying to track it down based on what the instruction was, it'll definitely help you out. Another important thing to take a look at when you're debugging your crash is the ERP. The ERP is the IO request packet, which basically bundles up all the stuff that you want to send to the driver, and then it's basically all the stuff that you want to send to the driver bundled up and passed down to it. And so you can look in here, and this is how you're going to find out what your input buffer was that the fuzzer sent. So you can see what all the random data that got generated that caused the crash was. This is also a chance to find out what the output code was. So in the case that you're fuzzing like 20 different outputs at once, you don't necessarily, or you need to know which one it is, because you're not going to necessarily know which one caused the crash. And that's definitely going to come in handy when you're trying to go through your static analysis phase. All right, now we just covered a fair amount of stuff relatively quickly, so let's kind of just see where we're at here. So first thing we did, right, is we located the drivers, then we brute forced all the output codes out of them, then we fuzzed the drivers, we got some crashes, and then we take a look at the crashes in WinDBG, try to figure out what's going on, got some relevant information out of the crashes, and now we're going to move to the static analysis phase. We're going to take this driver that we know has some sort of bug in it, we're going to try to dig in and figure out what that vulnerability is. And it turns out some of this process can be automated because drivers have a lot in common, a lot of shared traits between them. To talk a little bit more about that, I'll kick it back over to Adam.
Thanks. So as Braden was saying, you know, drivers do tend to share a lot of different structures in common, and sort of we wanted to create a tool to sort of help automate a lot of this reversing process, because what we noticed is while we were doing our research, we ended up reversing several different drivers, and we kept running into these same structures. And we're like, hey, this is like the 17th time I reversed this. This is getting old. And you know, the first thought is like, you know, it'd be cool if this was just automatically done for me, and I could just move on to where hopefully the bug is. And that was sort of the basic motivation for creating a tool. So that our first kind of like design idea for a tool is like, all right, let's make a tool that can automatically just take all these common structs and just identify them in IDA so that we don't have to deal with it. Cool. But then we're like, all right, well, should we just stop there? Or like, are there any other ideas we can kind of throw along with that to improve it, to make it even better? And so we had another idea, and the thought was, well, wouldn't it be nice to have the driver, when you just throw it in IDA, immediately tell you sort of like areas that you might find interesting as like somebody that's looking for security bugs? Things like, hey, where all these insecure C functions are being called, or where these commonly misused Win APIs are being used. By having that information, the sort of the thought was, even if you weren't like fuzzing the driver, but you're just straight reversing it, you know, you immediately know sort of like the shoddy areas of the driver. You can kind of look at it like, man, I bet if I poke this hard with this stick, it might die here. And that was sort of the thought process. And then another way to think about it was, like, let's say you do have a crash, and you know exactly where it happened in the driver, and those so happen to coincide with this path where these kind of not the greatest areas are located. It's possible that like, you know, those particular functions are responsible for the crash, or maybe you'd be able to use them to actually, you know, exploit the particular condition. And so that was sort of the reasoning on that. The other design ideas, now that we have a couple, we're like, okay, well, clearly we're going to have to build this tool with some type of, you know, language or framework of some sort. And we didn't want to make a brand new framework because we knew we wouldn't keep it updated. We're honest people. But we did decide to use an existing framework, and since we were already using IDA, we decided to go with that route and go with IDA Python. Now, of course, there's several different IDA frameworks we could have used, like IDA C, or our buddy Joe's rumored IDA PHP framework. Anybody? No? You should look for our GitHub, I swear. We decided just to go ahead and stick with Python. You know, Python seemed the easiest for our goals. And sort of like some other design ideas that we had were, you know, there's a lot of community work, I think, in this particular area when it comes to like building tools to help with these type of processes. And we didn't want to sort of rewrite the wheel. Like if there's already some functionality that exists out there, for instance, like decoding ioctals, like why we didn't want to just go ahead and rewrite that function since it's so many open source implementations of it and just wasting cycles. We're doing it and it's like we might as well share it. We're all community. And then like our final and most important design goal probably was to be easy to use. You know, if you have to take a 30-day training course or you know, read this Unix-sized manual instruction booklet to try to figure it out, then you sort of totally defeated the purpose of the tool, which was to improve your like efficiency and your time of use. And like you're not trying to like block people from using it because they don't have like speed reading abilities. And so with those design goals in mind, we decided to go ahead and go with calling it Driver Buddy, and I had a Python slogan. And sort of the first feature we decided to implement was the ability to identify the type of Windows drivers. Now, you may not know, but there's several different types of Windows drivers. There's function, filter, port, bus, file system. I mean, people probably can keep talking. There's several different types. And then additionally, they're also built on different driver frameworks. There's Windows Driver Framework, or WDM, and then there's also Windows Driver Model, sorry. And then there's Windows Driver Framework, or WDF, which is the more modern one, and it's really just a wrapper around WDM. And our thought was like, hey, if you could automatically identify that what type of Windows driver it is, you may have additional context, sort of like what this driver is doing in the system and whether or not you're interested in it or not because of how it plays its role. And so we noticed that there was some heuristics that you could do to sort of identify that. And so in this example, you can see highlighted, maybe you can't, there's a function, WDF version bind being used. And it just so happens that in WDF drivers are the only ones that use this function. Nothing else imports and uses this. And so this single piece of information tells us automatically that this is a WDF driver. And so we just sort of had coded that same functionality into our tool, and so we can automatically do that same level of analysis. The next idea that we wanted to sort of implement into the tool was the ability to automatically locate and identify and annotate the dispatch device control handler, commonly referred to as the ioctal handler. Now, as Braden was talking earlier, sort of how drivers communicate by passing ioctals down to the driver, which then eventually passes and reaches the driver, and then it gets handled and calls a specific function. So the thing that handles the IO codes that come in, that's the ioctal handler. You can kind of think of it as like this example. So you have like a power driver, and it has two specific functionalities, one ioctal code to turn on a monitor, another ioctal code to turn off a monitor. When the ioctal code hits the IO manager, it gets passed down the driver stack, eventually arrives at your driver. The ioctal handler is the one that does all the comparisons, like, hey, is this code for the turn monitor function on? No? Okay, go over here. Is this code for the turn off monitor function? Okay, go over here. Until it eventually routes it to the correct area in the driver. So you can sort of see how this would be interesting, why you'd want to know about this. For one, if you didn't have a way of brute forcing those ioctals, then you'd be able to reverse them out of this particular function. And as he said, Braden was talking about before, it might not be trivial. I mean, they may do some weird representation of the octal, some kind of math exam you'll have to take before you can figure it out, or go through like some crazy jump table. But the fact is, if you wanted to, you could reverse them out. Another thought is if you sort of use the methodology and you went through and you got a crash and you knew which ioctal caused the crash, now you have sort of like the starting entry point where the ioctal comes in and where the crash appears. And so you can kind of narrow your focus down into the area of the driver that this sort of crash is related to, assuming there's like concurrency controls built in this driver. And if not, then it'll be a total shit show, and we'll know about that later when we talk about the next driver. But yeah, I mean, that's the kind of like the reasoning we were thinking about. This is an important thing to know about. And so here's sort of just the demo of it doing its thing. And this is like a subroutine, not that important. But the highlighted region is the unidentified ioctl handler. So we run driver buddy, and it just identifies it. I mean, it's as simple as that. There's not really much to that particular thing. It's just, hey, it tells you where it's at, and you can go right to analyzing. The sort of next feature we wanted to implement is like, now that we have that one the real and most important kind of thing, we wanted to get all the rest that were kind of distinct to the different driver models. For instance, in the WDM drivers, there's a lot of these structs that are common that are part of the ioctl handler. Things like the device object, IO stack location, and the ERP. And then in WDF drivers, there's just like a plethora of functions that can automatically be identified just based off KMDF string. And so here's just another demo of sort of that functionality. This is another like unimportant function. It actually turns out this is the ioctl handler from the previous slide. We just stepped into it. So it's not identified or anything. We run driver buddy. It kind of goes through and does its analysis of some sort. And then it comes out and it's now identified, hey, yes, this is the ioctl handler. Also, there's some ERP information, a device object, and some IO stack stuff, which is cool. And then in this one, this is a WDF driver. And if you remember from before, the reason you can tell that is it's calling WDF version bind. And additionally, that's pretty much all we can talk about it. I mean, it's kind of not much going on in this function. We don't really have a lot of context. It's a really tiny snippet. And then these two highlighted quad words. We're like, well, those are probably functions, but what are they? I don't know. And maybe if you like do kernel development for a long time, you can just look at this and just know what it is. I know I can't. And so unless you want to do all the analysis around this thing to try to figure what those are, you know, you're probably going to be at the same spot where you don't really have much context. Yep.
Was it data structures that you guys had to write out yourself, or was that part of IDAPRO?
Yeah, so IDAPRO has a lot of built-in structs already, and so what you can do is you can utilize sort of like this undocumented feature of IDA. It's like called like IDA TVTIL or something like that. I had to look into the C source to find it. But basically, you can use that to actually use those and hook it. But you still have to like identify like, hey, where these are and offset to like the device object pointer or whatever it is that you're passing in. Cool. So yeah, there's not really much context about what's going on in this. Luckily, it turns out that those two specific functions are WDF functions. And so after we run driver buddy, they automatically get identified. And so like now, before we really had no context about what was going on, we can actually Google or MSDN these functions, find out what they mean. And those are usually like real sticking points when you're doing reversing, is when you're just like, man, I don't know what these function pointers are. What is this going on? But now we know, and so hopefully we can continue on with our analysis. Sort of the next thing we wanted to implement was the ability to decode ioctls. Now, this isn't unique. Tons of tools do this. In fact, the fuzzer we use, DIBF, already has this built in. But we thought it was a useful feature, and we wanted to include it anyways. And you may be asking, okay, like, well, what is decoding ioctls? What does that even mean? Well, it turns out that ioctls are deterministic. So they kind of have this format where part of the data gets represented in this manner. So there's like the device type, the required access, the function code, and the transfer type. And sort of for the purpose of like what we're focusing on, we're really going to pay attention to the transfer type only. And so what the transfer type does is it's how the data from the ioctl gets transferred to the device driver. And there's four main modes. There's a method buffered, and method buffered is where the data gets transferred to a kernel land buffer. And then there's method direct, indirect, and method outdirect, which is uses memory descriptor lists, or MDLs. And then there's method neither, which, spoiler alert, does neither of those. It actually just copies and it reads and writes directly to user land memory, which I don't know how much you guys know about stuff like that, but that should be sending some weird tinglies to you. It's not the greatest idea for a driver to use such a thing. And that's sort of the reason why we wanted to include it. You know, if you got a crash, you sort of followed this methodology, threw it into IDA, you know the ioctl, you decode it, you find out, hey, this is method neither. you're immediately going to be game-faced because you're like, oh yeah, I got that exploit now, baby. And that's just sort of how that comes out. And so at the bottom there is just an example of it being decoded. It's not unique, yay. And then the last thing we wanted to do is kind of like that interesting areas of the driver function, and which is sort of subjective, but we kind of focused on insecure C functions and commonly misused Windows API calls. And so here you can kind of see it looking through. This driver is pretty boring. It didn't really have much going on. But it does flag some Win API calls. Now, I want to be clear that the fact that they're using these Win API calls doesn't mean it's a bug. These are like commonly used normal Windows API calls. It's because developers can sometimes misuse these that we want to flag them because it can be interesting. Specifically, like if you find a way to control some way with these Windows API calls, it can become very interesting. Things like object referencing and dereferencing. These can lead to ref counting exploits. And so those were sort of the features that we came up with on this initial idea. And we used it, kind of like continue to do our research and reverse engineered the drivers, and we came up with some bugs. And I'm going to go ahead and turn it over to Braden to let him talk about those bugs.
So, yeah, bugs. Let's talk about them. So we did find a couple of unique vulnerabilities in a Lenovo driver, and they ended up issuing an advisory for it. And we'll go into a little bit more detail on them, but one was a race condition bug that ended up in use after precondition, and then the other one is an unsanitized input that ended up giving us a arbitrary memory read. And we have some other crashes and things that we think look like they could be vulnerabilities, but right now they're just kind of like bugs. We haven't had a chance to follow up on them, but hopefully someday in the future we will have more to say about those. Before we go any further, just want to give a shout out to Lenovo. They were super great to work with during the disclosure process. They emailed us back the first day we emailed them. Within a week and a half, they had sent us like a beta patch to test out, and I think like a month and a half later, they had the full patch out and an advisory posted, which we thought was pretty nice. So kudos to them. 10 out of 10. Would report again. And now that those bugs are patched, we can give you a tale of two POCs. So the first issue is this race condition bug, and you can see here it was memory getting referenced after it was freed in the special pool. So the special pool, if you recall, is a sure sign that our friend driver verifier is what caught this. And so one thing to keep in mind with drivers is that they're asynchronous by nature. You know, every different user, every different process can be calling them at once, which is not necessarily a problem as long as there's no shared memory, which also isn't really a problem as long as there's concurrency controls. But in the case of this driver, I had an object or a queue full of objects that is shared between all callers and had zero concurrency controls around it. So what would happen is you could be removing stuff from this queue while some other call is using that same object, and so you'll remove it and then they'll use it after it gets freed. So what can we do with this? Well, it looks to us like it's exploitable for code execution, but we can't say for 100% sure because we ran out of time and we were trying to get that working. For a quick and dirty local denial of service, you can just run something like this where it's just a few threads adding and removing objects at the same time. And this will actually cause your computer to blue screen about as fast as it takes the computer to load a blue screen. So our next bug is the memory read, and we did spend a little bit more time diving in on this, so we'll go ahead and go through kind of what this looks like in the driver itself. So this is the ioctl handler that we were talking about, Adam was referencing earlier, and you can see that the herb is for us by driver buddy. And so this is where your data first comes into the driver when you send that device IO control call. This is the handler that picks it up. And the important thing to keep in mind here is that the herb is going to have the system buffer that contains all of our potentially malicious data, as well as the ioctl code that's going to tell it which routine to send our data to. And so this is what the ioctl handler looks like at a high level. And the main thing I just want to point out here is this kind of cascading effect up in the top left, where it's kind of what it's doing there is it's saying, hey, is this ioctl code go to this routine? No? All right, go down here, check this one. Does it go to this routine? No. So on and so forth, until it gets to something like this, where it says, hey, this is the ioctl code I'm looking for, and it wraps up and it takes all your stuff and passes it to the appropriate routine. So I recognize this one's probably pretty hard to read, but basically all that's going on here is the driver is checking to see if our output buffer is big enough to hold the data it's planning on sending back. The important thing to keep in mind here is we want to make sure that we pass all these checks, so that way we can get into this part, which is the important part. So this is the function where the vulnerability lies. And so what happens here at the start is you get this how function call, and what that'll do is it'll return a physical address to us every time we run this. Return the hex number fed 10,000. So then what happens is it takes this number and it adds it to a number that's in our buffer that we control. And then it takes the sum of that addition and passes it to this in-map IO space down here. Way down there at the bottom. And because of the properties of like kind of integer math, right, we can actually now fully control that first call by like overflowing the number with our addition. And so we now have full control over the first call to in-map IO space. So you might be wondering, what's in-map IO space? Why do we care? So in-map IO space, what that does is it takes in a physical memory address and then it maps it to virtual memory, and it gives us back a pointer. And in the case of this driver, what it does is it takes in this address that we give it, that we now fully control, it maps it into virtual memory, it reads 8 bytes, and it sends it back up to the user. And so what we can do is just call this over and over again, incrementing our buffer 8 bytes at a time, until we have actually read 4 gigabytes of physical memory, the first 4 gigabytes of physical memory. And that's exactly what we ended up doing. So you can see here in our little proof of concept, it's just a for loop, and we just make this call over and over again and we check to make sure that it's not all zeros, because it turns out a lot of physical memory is uninitialized. But we write all this to a dump file. And so after we get through and get our first 4 gigabytes of physical memory, what are we going to do with that? So there's a few things you can do with a giant swath of memory. You can use it to bypass kernel ASLR by identifying various kernel structures. You can also use it to read secrets that your process should be able to read, passwords that are cached by other processes, encryption keys that might be laying around, or, for instance, your BitLocker keys that might be hanging out in kernel memory. Or you can do a trivial local denial of service. And so what we decided to do was try to see if we could recover our BitLocker keys out of the dump file. And talk a little bit more about that. I'll kick it back over to Adam.
Thanks. So, just a real brief overview of what BitLocker is for people that may not know. BitLocker is full disk encryption option for Windows. It basically uses a family of AES encryption algorithms to sort of secure the data. There's several keys involved, but we're really going to only focus on the full volume encryption key, because that's what we needed to actually decrypt the drive for our example. And then how it works is when you log into your computer, you undo the BitLocker screen, and you're using it as it's still enabled. It actually only decrypts the portions of the drive that are in use. So the other parts of the drive are still encrypted. And so this tells us immediately that those keys for encrypting and decrypting are going to have to be somewhere where we can get access to it quickly, because it's going to be doing it all the time. And so we knew by that alone it was going to have to be in memory. And thus, we have a memory disclosure bug. Kind of a good combination. And so we're like, all right, cool. So let's just go ahead and grab those BitLocker keys. I'm sure that they're easily able to be located. But it's not like the BitLocker keys sitting there with a sign on it. Yo, what's up? BitLocker key in memory. It's just like random bytes. It just looks like anything else that would come out of an encrypted function. Just a bunch of hex numbers. So we're like, all right, what are we going to do? Well, luckily we didn't have to do anything, because somebody else has already done all this work for us, which is super awesome. And we just kind of followed along with the heuristics of what they came up with. And this is sort of what it was. It's sort of a lot of technical information about how these heuristics go together. We wanted to make sure that it would work on our system. So our system was a fully patched Win10 installation with a AS128 cipher and CDC mode. And the main thing to kind of narrow down where the BitLocker keys would be in memory there's 2 specific things that really narrow it down. The first is the pool tag. So for people that aren't familiar with what pool tags are, when driver developers are creating their drivers, anytime they're doing memory allocations, they have the option of adding a pool tag to that memory pool allocation. And what this is, it's a unique string of some sort that they can use to essentially help them debug it later on. Because when you get a crash dump, and you have all this like pools of memory, like, oh God, how am I going to find my pool? Well, they have this like unique tag they can search for. It's like, I am super dumb. I'm sure there's only one of those tags. And then you can come up and it shows only those pool tags. And so that, for this particular driver, was the CNGB for the BitLocker keys. Now, the CNGB is actually associated with all of Microsoft's crypto API calls. So like all the new ones, which is like cryptography next generation, I think is what it stands for. And so that's not really like going to narrow down enough, right? There's going to be like a ton of crypto API calls. You're going to have like 1,000 pools tagged with this thing, so it's like not enough. But the second piece, the pool size, is what really narrows it down. So it turns out, for at least our tests, and it seems like many other systems, that BitLocker keys are always allocated into pools of 672 bytes. So these two pieces of information really narrow down the scope of how to find the actual BitLocker key in memory. It's not perfect because those two alone don't really get it. And what we ended up doing is we ended up finding some own heuristics that weren't added along to this, that weren't really shown on the person that we were looking for information about this on. And this is kind of like what we came up with. So in red, you can kind of say this is the pool tag, that CNGB. I don't know if you guys can still hear me. And then here we have the 672 byte green pool size. And then what we noticed was, if the pool allocation was going to contain the BitLocker key, it's going to be anywhere between 0x40 and 0x90 bytes from this allocation. So if it's not between like that many number of bytes, then you're not going to see it in that pool. It just doesn't exist. And I don't know why. I couldn't tell you. But if it is, you will see the pool, the actual key size, which is going to be either 128-bit or 256-bit, depending on what you chose for your encryption algorithm. And then after that, you will always have these 3 null bytes. And that's sort of like another indicator, followed by the full volume encryption key. And then there will be 4 null bytes, followed by a duplicate of the full volume encryption key. You're like, why are they doing this so many times? I can't tell you. But that is how it comes out. And those particular set of heuristics were always correct. I mean, every single time if you use that, you'd always find the BitLocker key, which is awesome and terrifying. So what can you do with a full volume encryption key that's extracted from memory, right? It's not like BitLocker gives you the option like, hey, go ahead and decrypt this with weird bootlinked key. It's not like one of the standard options. So we, luckily again, we had some work done by some other people that created an open source library to mount BitLocker drives in Linux, libbde. And so that's exactly what we did. So here's just an example slide of us, hey, this is actually a BitLocker encrypted drive. It's the AES-128-bit, just like we were talking about. Again, this is just more of the same. Like, yes, this is encrypted. You can tell it has the full volume encryption header at the top, and then a bunch of encrypted garbage. And now the important slide, right? The actual decryption process. Now, if you have like super eagle vision, maybe you can see that that is the same key we pulled out, but you probably don't. You'll have to take my word for it. It's the same key. And we use that to mount the drive. It decrypts. And then we're like, okay, what can we do to like prove we decrypted this thing? Like, you know, we obviously know that there's going to be some information on the drive that only we'll know. So we knew we had some secret information in there. So we decided, all right, we'll just search for that. So it turns out we knew the identity of Satoshi Nakamoto. So, spoiler alert, everybody, Satoshi Nakamoto is Hollembaek. Sorry. And then, just all jokes aside, we came up with just some more, metadata. We wanted to show the name of our computer was Sub-Zero. We just looked through it. So, yay, it was decrypted. We did it. Good job, us. But what we really were really looking for out of this, after coming up and saying, hey, this does work, was we wanted to see if other people were interested in this kind of work. And so, if this is something you find interesting and you would like to keep, kind of do it on your own or try it out, then this is sort of a breakdown, TLDR edition, of how you can do this. So you have, first you want to find your drivers, locate whichever ones they're going to be, Microsoft, OEM, whichever you're targeting. You can use tools like Driver Query and WinOps to help you out here. Next, you're going to either have to brute force the ioctls or reverse them out of the driver. Once you have those ioctls, you can start fuzzing the drivers until you get some crashes. Once you have some crashes, go ahead and triage them. Take as much information as you can. The crashing, what input, where it happened in the driver, what's the IOCTL code, what kind of violation was it, and then see if it's exploitable. And if it is, make a bug. And so basically, that's the majority of our talk for this. We have some future work we'd like to follow up on. We wanted to, obviously we have some bugs we haven't had a chance to triage. We think a couple of them are pretty cool, and that will turn out to something interesting, but haven't actually got that point yet. We would like to do some sort of automation in the WinDBG scene, kind of like the same idea, to help automate the crash triage analysis portion, make things easier and faster. Anytime you can improve efficiency, it's better. And then sort of the rest of the things are like we like more driver buddy features and driver and then hit-based trace flushing. Yeah, sure, okay, someday. But thanks for listening, everybody. I do really appreciate it. Special thanks for DerbyCon and everybody else on this list for helping the research. As far as the tools go, both DIBF's fixes that we've sort of made pull requests for and driver buddy will be released very soon. Thank you.
So the drivers who found the bugs in, did they make it through the WCL process? Were they WCL certified or were they not?
So the Lenovo drivers, they were signed, as far as I know, that they had to have gone through that process. Yes?
If you're posing in a DM and you use BTD and still fuzz the drivers, have you had any luck with that?
I know we haven't tried that ourselves. Do you have anything to add on that? No. We haven't tried that ourselves, so I couldn't comment on that. Cool, thanks everyone.